Bank manager has developed a new system to reduce the time customers spend waiting for teleservices during peak hours. Suppose the manager wishes to use a random sample of 100 waiting times with a sample mean of 5.46 and a known population standard deviation of 2.47 minutes. To support the claim that the mean waiting time under the new system is different than 6 minutes. Is there evidence to support the manager's claim? The first thing we always do at a problem like this is we develop a hypothesis. So I want to know, what does the population mean? What is mu equal to right here? Well, when I read this, they want to support the claim that the mean waiting time under the new system is different than 6 minutes. So mu is equal to the mean, we'll say the mean waiting time. And when I write this, then my null, HO or H0, is that mean waiting time is currently sitting at 6 minutes. I want to test to see if it's different than 6 minutes. I'm going to say mu does not equal 6. That is the hypothesis to be tested. Either the mean is 6 or the mean is not equal to 6. The next thing I'm going to do is I'm going to say my Z. I need to calculate a Z-score now. So your Z-score, Z is equal to X bar minus mu divided by sigma over the square root of n. So when I plug all this in, here's what I'm going to get. I get my Z value. Z is equal to my sample mean, 5.46, minus my hypothesized mean, the population mean, which is 6, divided by the standard deviation of the population, 2.47, over the square root of my sample size, which is 100. So that's the first part. Calculate the Z-score, right? So when I calculate this, 5.46 minus 6 is this, divided by 2.47 divided by the square root of 100. Here's my Z-score. Negative 2.186. Negative 2.186. Now, there's a couple ways we can do this. They have not given us an alpha value. Generally speaking, if an alpha value is not given, we will always set alpha to 5%. That's the default alpha level. The default alpha level. Everybody got that? So what I've done now is I've just found a Z-score. And here's what I know. I know my alpha is at 5%, right? So my inside would be what again? What's the inside here? Anybody? You guys still there?
95.
95, thank you. The inside is 95%, right? And we know that the Z-star that corresponds to 95% is 1.96. That means I need to look at the also other side of it, which is negative 1.96. The question is now, where is this negative 2.186 falling at? Is it falling into the safe region, the plausible region here, the fail to reject region, or is it falling into the rejection regions? Where does that negative 2.186 fall at?
Rejection region.
Good. It's falling in the rejection region out here. This is negative 2.186. So based on this, because it's falling in the rejection region, we're going to reject HO. We're going to reject the null. Why do you reject the null? How do you reject how do you reject a person's innocence? There has to be enough evidence to support their guilt. So there is enough evidence to support H1. There's enough evidence to support H1. Now, that's one way to do this. The second way to do it is to use the actual alpha value right here and do it and run a test. And so when we do it that way, let me show you how to do it that way too. What we're going to do now is we need to find a probability. We need to find a probability for this right here, for that z-score. I want to find the probability of finding a z-score that's not equal to negative 2.186. Now, the way we do that then is we need to use the norm.dis function in our calculators. The norm.dis function here. And when I go to my Excel and do that, remember, I have a function called norm.dis, and it calculates areas. So I want to do norm.dis. The x here is, I'm calculating up to that value. So I'm always going to calculate, I want to calculate negative 2.186. The mean of the curve is 0. The standard deviation is 1. Cumulative, you set to true. Here's the actual p-value on the left of negative 2.186. So the amount of area that sits on this side of negative 2.86 was 0.0144. That's the amount of area that sits on that side, which also means that the amount of area sitting on this side, because you can also check over here at positive 2.186 is what? What's that? How much area is over here? You have to check both sides actually. How much area is over there? 0.0144 again. So the total area is what I'm actually interested in. The total area is what I'm actually interested in. Did not do that right. That's at 0.1044. What you have to do is you just double that value. And here's the actual area. I'm looking at 0.0288. What this represents is the probability of getting an unlikely value as extreme or more extreme than negative 2.186. That represents the value of getting that value as extreme or even more extreme of negative 2.186. And so what happens now is this: when we go and we compare it, our alpha value is at 0.5. This right here, this value right here is the p-value. You've just calculated the p-value, the unlikelihood value. So I'm going to compare that 0.0288 that's less than 0.05. It's less than the unlikely value. Because it's less than the unlikely value, guess what we do again? We still reject HO. We're rejecting the null hypothesis here because my p-value is less than the alpha value. When the p-value is less than alpha, you always reject HO. That is the rejection rule there. So you can do it either way. You can do it through a critical value method, which places you in critical regions like this, it's rejection regions, or you can use the p-value and calculate it like this, where you compare it to your alpha value. If the p-value is less than alpha, you reject. If the p-value is greater than alpha, you fail to reject. If you reject, remember you're rejecting because there's enough evidence to support H1. If you fail to reject, there is not enough evidence to support H1. So the last thing I want to talk about is going to be our errors. Yeah. And here's what happens in any kind of hypothesis test. If we reject or fail to reject that a person is innocent, for instance, in court, there are two possible errors that can be made. If I reject a person's innocence and they are truly innocent, I have made an error. If I fail to reject a person's innocence and they are really guilty, I have also made an error. The question is, which error is worse? Do you think rejecting an innocent person's innocence, which means that you're basically locking up an innocent person? Do you think that is worse than failing to reject a false person's innocence, which means you're letting a killer walk here? Which error is worse, locking up an innocent person or letting a killer walk? Anybody got an idea there? No, you ain't got no ideas there.
Letting a
care.
killer walk.
Good. Thank you for saying something. Everybody agree with that then? The other 8 people on the call, y'all agree with that?
It's either
Letting a killer walk is the
innocent
worst error. So locking up an innocent person might be worse to some people, right? Yes.
Yeah.
Yes.
Yeah. I mean, it just depends on who you are as a person, to be honest, which one's worse, right? But here's what happens. When we look at this, here's what can happen. The person is either innocent or they are guilty, right? They're innocent or they're not innocent. They've actually committed the crime or they haven't. If they're innocent, this means that HO is true. If they're guilty, that means that HO is false. Why is that again? HO is true means the person is what? Really innocent. HO is false means the person is really guilty. Here's what happens. The person actually committed the crime and HO is true. Y'all got that? If the person has committed the crime and HO is really true, that means that the innocent person, the person committed the crime, they're the killer. You found them innocent, you let a killer walk. That's known as a type 2 error. If a person did not commit the crime and they're found innocent, that is a correct decision. If a person is guilty and they committed the crime, that is also a correct decision. If a person is guilty, but they did not commit the crime, they're innocent, you're locking up an innocent person. That's known as a type 1 error. So here's what has to happen. For a type 1 error to occur, type 1 error, this is when you reject a true null hypothesis. What does that mean? If I reject the true null hypothesis, I've rejected your innocence, which means I'm saying you are what? Guilty. I rejected your innocence. I'm saying you're guilty. But the null is really true. You really are innocent. So you're really innocent, but I've rejected the innocence. I've locked you up. You are a innocent person that got locked up. That's called a type 1 error. A type 2 error and a type 2 error, here's what we do. Type 2 error, you fail to reject a false null hypothesis. A false null hypothesis. Remember, the null is that you are innocent, right? A false null would mean what then? You are not innocent. But I have failed to reject that, which means I'm still saying that you're innocent. So you are really guilty, but I'm saying that you are innocent. I'm letting a killer walk. And these 2 errors, type 1 is called it's actually made, the percentage of time we make type 1 is when we set that alpha value there. Type 1 error is really alpha. So if I say my alpha is 5%, that means I'm okay with locking up an innocent person 5% of the time, as long as the other times I get the amount of killers correct and the amount of other innocent people correct as well too. So 95% of the time I'm going to be right, but 5% of the time I'm going to lock up an innocent person. A type 2 error is called beta. Beta leads us to this thing that we call power. Power is equal to 1 minus beta. And power is this is the ability of a test to correctly reject a false null hypothesis. What do I mean by that? You're really guilty. We go to court, evidence comes out. I find that you are really guilty. I reject that false null. I've done the right thing. That's called power of a test. The power is very high. Then you think about this in terms of percentage, 1 minus some percent. Beta is this is basically a percentage, by the way. If you want a very high power, you want beta to be very small. You want the beta error to be very small. Well, what is my beta error again? My beta error is
5%.
Yeah, but that's the alpha error. Beta is letting killers walk. This is the beta error. I want that error to be very small. I want it to be very small. Is everybody saying that? I don't want to let a whole lot of killers walk. What do I do in a real court system? What would I do then? If I don't let a lot of killers walk, that means I need to lock up what? A lot of people, right? Because if I'm locking up a lot of people, what am I guaranteeing myself? That I'm probably going to lock up what?
Innocent people.
A lot. Good. I'm locking up a lot of innocent people. I'm also going to lock up a lot of killers, though, right? And I want you to understand. You said it right there. The alpha error is that you lock up innocent people. So I want you to understand this because somebody just said it. What ends up happening is this in this particular thing. I want this error to be very small right here. I want to let killers walk being very small. In order for that to occur, then I have to lock up more people. Well, naturally, if I lock up more people, what am I also going to lock up? I'm going to lock up a lot more innocent people as well. So if we decrease the beta error, it's going to increase the alpha error. It's going to make me lock up more people. That's naturally how it has to work. Likewise, if I say that, hey, locking up innocent people 5% of the time is way too much, I can decrease my alpha level. And as a matter of fact, alpha is the level that you can set however you want to set it. So I can say I don't want to lock up innocent people 1% of the time. But in order to lock up innocent people 1% of the time, what does that mean? I got to let more people walk, right? Who am I what kind of people am I letting walk more now? I'm letting my killers walk more. So here's what happens then. There's an inverse relationship that exists between alpha and beta. And what I mean by that is this. As you increase alpha, or really what we say like this, as alpha increases, beta decreases. So if I want to have a small type 2 error, or if I want to let less killers walk away, I have to be okay with locking up more innocent people. So I have to move from 5% to 10%. Because if I move from 5% to 10%, I'm gonna lock up 10% of innocent people. But guess what? I'm gonna lock up a whole lot more killers too. Or the other way is true too. As alpha decreases, beta will increase. Tired of locking up innocent people at 5%, I'm gonna start locking them up at 1%. If I lock them up at 1%, what starts to happen? Well, I'm locking them up a lot less, which means I'm locking up a lot less killers as well. And so here's what happens. If I want the power of the test, the ability of a test to, I don't know why I have an or. That should be to correctly reject a false null hypothesis. So the ability of a test to correctly tell me somebody is guilty. That's what the power is. If I want that to happen, I want this beta value to be as small as possible. Well, how do I bring beta down? I have to increase alpha. Bringing beta down, because what happens is this will be 1 minus some really small number. It'll make for a large percentage. You can think of this as being a percent, by the way. We don't ever really calculate power, but you can think of it being a percent. The higher the percentage, the better your power is. In this particular case, if I do 1 minus a really small number, for instance, if I do 1 minus 0.25, that's 75%. If I do 1 minus 0.75, that's 25%. I'd rather have a 75% power test than a 25% power test. So I want this beta value to be as small as possible. To do that, I have to increase alpha. I have to increase making this error of locking up innocent people. That's real life, by the way. So I did that. Talk about that. Let's look at an example. Pharmaceutical researchers are testing a new drug for acne. Severity of acne is rated on a scale of 1 to 7, with 7 being the worst. Side effects of the new drug may include vomiting, upset stomach, mild fever, or hyperactivity. The company is marketing a new drug that they believe will substantially clear up acne, being a 3 or better. So if you have a 7 being the worst, that means anything, they're going to make it to where it's a 3, 2, 1, or 0, or 3, 2, or 1. Anything worse than a 3, better. I mean, anything that is greater than 3 is still not any improvement, what they're saying. From the company's standpoint, what is a type 1 error and what is a type 2 error? What are the consequences of both errors? So here's what we say. First off, we need to develop a known alternative. HO is that we'll say this, mu is equal to 3. Right? Mu is equal to 3. In this particular case, HA or H1 is that mu is less than 3. We haven't talked about directions, but this is less than 3. What does greater than 3 mean? What does equal to 3 mean? Technically, we can do, let's do it like this. Greater than 3. Greater than or equal to 3. Greater than or equal to, technically, let's change this number. Greater than or equal to 4. Less than 4, because those are whole numbers. There we go. What does greater than or equal to 4 means? That means that the scale came back 4, 5, 6, or 7. That means that there is no improvement, right? They gave you on the scale 4, 5, 6, or 7, there was no improvement. Here, less than 4 would be 3, 2, 1, or 0. That means that it was an improvement. So there's no improvement versus an improvement. Here's what happens. They want to know what is a type 1 error. Type 1 error is locking up an innocent person. Null is that the person is innocent. Remember that the person is innocent, right? If I lock up an innocent person, what does that mean? The person is really what? What is the person? The person is really what?
Guilty.
No, the person, if I'm locking up an innocent person, the person is really what? They are really innocent. But what did the test say or the evidence say? The evidence said that they were guilty, right?
Guilty.
So look here, here's what happens then. In this particular case, a type 1 error would be, there really is no improvement, right? There really is no improvement. So that's how we start this. There really is no improvement. What does the test say though? How do you make the error here? There really is no improvement. How do you make the error? The test says what? The test says there is an improvement. That's a type 1 error. There really is no improvement. But the test says that there is an improvement. How did the test do that? We reject a true null. We reject a true null. That's what that really says. There really is no improvement. Test says there is an improvement. We have rejected a true null. What have we done then? We are giving what? We are giving people a drug that really does not work. We are really handing out a drug that really does not work. Does everybody understand that's what this is saying? This is literally saying the drug does not work. There really is no improvement. Test says there is an improvement. You reject the true no, the drug does not work. And I'm getting that from my null and alternative, by the way. My null says that if a value is greater than or equal to 3, I mean greater than or equal to 4 in this case, which means that it's less than 4 here. Greater than or equal to 4, there's no improvement. Less than 4, there is an improvement. I'm hoping to show this right here, by the way, that it's less than 4. Type 1 says then there really is no improvement. So this is already true. That's what a type 1 means. This is true. But the test rejects it and says that this one is not what I'm going to take. And a type 2, here's what happens. There really is an improvement. There really is an improvement. But look what the test does now. The test says, there is not an improvement. So there really is an improvement now. The null this time in this particular case, the alternative is actually true. There really is an improvement. But the test says that this is true. There is no improvement. You have failed to reject. What you're doing is you're failing to reject. You fail to reject a false null. You have failed to reject a false null hypothesis. Failed to reject. All right. You failed to reject a false null. The null is false. What do I mean by that? What is the null again? There is no improvement. This is false. There really is an improvement. But you failed to reject that. You failed to reject this no improvement statement, which means you're saying that there really is no improvement. Which means that now what happens here, you have a good drug, but you throw it away. You throw away a working drug. You throw away a working drug here. What are the consequences of a type 1 error? What happens if you give a drug out that does not work? What happens there? Look at the side effects of the new drug. They may include vomiting, upset stomach, mild fever, and or hyperactivity. What have you just done? You're passing out a drug that does not work, and you're giving people these side effects when the drug does not work. That's a pretty bad thing to do. The other one, type 2, you throw away a working drug, right? The drug works, but we think it doesn't work. So what do? We throw it away and start all over again. Well, what happens? Well, we don't get a chance to sell our drugs, so we're going to lose money. We're throwing away a good product, we're going to lose money. People aren't going to have a chance to buy our product, we're going to lose money. So type 1, a type 1 error is going to affect who? Who does the type 1 error affect? The consumers or the producer? Anybody answer that question for me, please?
Mostly the consumer.
If I make the consumer, it's going to affect the consumer, the people who actually take the drug. It's going to hurt them. Type 1 errors are called the consumer's risk, by the way. They're called a consumer's risk because when they occur, they affect the people consuming them. A type 2 error affects the producer's risk. It's called the producer's risk because the producer is affected by it because they're not making money. In this particular case, which error is worse, type 1 or type 2? Anybody answer that? What's worse, giving people a drug that doesn't work or throwing away a working drug?
Type 2.
From the producer's standpoint, throwing away a working drug is worse, probably, right? From the consumer standpoint, though, the drug not working, giving you adverse side effects, it's probably the worst error. In general here though, I would probably say a type 1 is the worst error because you're giving people a drug that doesn't work and are getting these side effects from that particular drug. That would be like with the COVID vaccine right now. People taking the COVID vaccine and it's not working, and them thinking that it does work, or them thinking that they take the particular vaccine and it gives them all these side effects and it's not working. That's a lot worse than having a vaccine that doesn't work, or having a vaccine. I guess it's not really. I was gonna say it's a lot worse than having a vaccine that works and throwing it away and starting over. And you're right. It just depends on what you're looking at it from. Sometimes there's not really a real like definitive what's worse and what's not. Most of the time, though, when you start talking about it and on your homework, I think it'll ask you from a standpoint, from the producer standpoint, which one is worse, from the consumer standpoint, which one is worse. Most of the time, type 1s are worse for the consumer, type 2s are worse for the producer. All right, that should be everything you need